Our final section of this chapter is to look at some of the reactions of aldehydes and ketones. And as we've said with every other functional group that we've studied, that these are just a small number of the reactions that these functional groups do. But we focus on these because they're some of the most important ones, and they relate towards things like biochemistry more than some of the ones that we don't cover do. Now, for most reactions of aldehydes and ketones, we talk about the two functional groups together. And the reason that we do that is because for most reactions are the same, or largely the same, between the two functional groups. There are a few that are not, and we'll talk about at least one of those. But most reactions that apply to aldehydes apply to ketones in very, very similar ways. But the first one we study will be one of those exceptions, and that's oxidation. And this really is only applicable to aldehydes. Now, you may recall that when we were talking about oxidation of alcohols, that we said with a primary alcohol, it gets oxidized to an aldehyde, and then under certain conditions, that aldehyde gets oxidized further to a carboxylic acid. Now, sometimes that's something we want to happen, and sometimes we don't. Turns out this oxidation isn't that difficult. Now, where does the term oxidation come from? Well, it turns out these are reactions that originally were found to occur with oxygen. And many of them, they still can. It's just, in most cases, that's not the way we do them because it's not terribly efficient. It takes a lot longer for the reaction to take place in that way. But aldehydes are chemicals that you often have to be very careful with. If you leave a bottle of aldehyde, something like benzaldehyde, sitting around for a long enough time, you may start to see a white solid in your bottle of benzaldehyde. And what's happened is that your benzaldehyde, slowly, over time, has at least started to have some of it oxidize, just sitting out in the air, to benzoic acid. Now, it's a slow process, but it's still one that we have to account for. But as we said, in some cases, this is something that you actually want to do. In fact, probably the best known case of this is what's known as a tolerance test. So I know with this course, there's many of you who are taking just the lecture and not the lab. But one of the things if you were taking the lab, one of the things you often have to worry about in the organic lab is, all right, I've run this reaction and I've made some product. Unfortunately, my starting material was a white solid and my product is also a white solid. So how do I know if this reaction did anything? How do I know if it worked? And so we have a lot of techniques in the lab, a lot of instrumentation that lets us figure that out. Different ways of analyzing the molecule that show us, yes, a reaction took place, or no, it didn't. Years ago, though, those techniques didn't exist. And so in those days, how would you have determined if a reaction took place? And in those days, you often did what were called chemical tests. And these were basically very simple reactions that you knew took place with one functional group, but not another functional group. And you could use these to do sort of a very quick test to see what kind of functional group was present. And aldehydes actually had one of the easiest tests to do. And while we don't rely on these types of chemical tests anymore, this is one that you still could do quite easily. So how would you do this? Well, the way that you would do this is what was called the tolerance test. And in a tolerance test, you take an aldehyde and you add a silver reagent to it in the presence of base. And if you had an aldehyde present, the aldehyde would react with the silver reagent to make carboxylic acid plus silver metal. And so if you ran this, if you added these reagents, which are commonly referred to as the Tollens reagent, if you added them to an aldehyde, as soon as you added them to an aldehyde, you'd get silver metal to precipitate out and say that you knew you had an aldehyde. On the other hand, if you had some other functional group, you wouldn't see any silver metal come out. But this is also a method that, while we don't use it for chemical tests as much anymore, we can now use it for oxidizing an aldehyde to a carboxylic acid. Our next reaction is reduction. And if you recall previously, we learned about the oxidation of alcohols to form carbonyls. So this is the opposite of oxidation. So if you reduce an aldehyde or a ketone, we're going the other direction. We get the alcohol back as the product. And we see examples of these biologically. Again, when you're looking at any sort of biological pathway, when you see reagents like FAD or NAD, that often tells you that some sort of oxidation or reduction is taking place, and you might see this direct reaction in one direction or the other. How do we do it in the lab, though? Well, there's a few different ways that we can do it, but the most common method is to use hydride, H-. Now, we don't usually use H- itself. While you certainly can and actually can purchase a reagent that has H- in it, that's not something that we use that often. What we use instead are reagents like NaBH4 or LiAlH4. And the key in both of these reagents is that for both of these reagents, the element that hydrogen is attached to, hydrogen has an electronegativity of 2.1, whereas boron is 2.0 and aluminum is 1.5. So these bonds are polarized towards hydrogen. And that's fairly unusual. We don't see a lot of reagents like that. And so these reagents, especially the aluminum-based one, behave as if they're H-. Now, H- is extremely reactive, and so these are reagents you have to be very, very careful with in the lab. But these reactions work extremely well. They're very, very reliable. And again, you can take your carbonyl, your aldehyde or ketone, and add one of these to it. And as a result, you get an alcohol. Now, does it matter which one you use? Does it matter if you use the first one, sodium, which I have pictured here, sodium borohydride, or the other one, lithium aluminum hydride? So in the long run, it doesn't really matter for aldehydes and ketones. Both of them have very, very similar behavior when they're reacting with aldehydes and ketones. Now, in the next chapter, when we talk about reductions of things like carboxylic acids and esters and amides, in that case, yes, it matters, and it actually matters quite a bit which one you use. But for aldehydes and ketones, you can use either one. Most of the time, we prefer sodium borohydride, and that's just sort of for the simple reason that it's a much safer reagent to use in the lab. But again, this process of reduction is pretty much identical, except for being the reverse to what we saw for the oxidation of alcohols.